Welcome back to the deep dive. We talk a lot about speed, efficiency, but today we're really hitting, well, kind of an inevitable wall. The whole race for faster computing, it's bumping up against some hard physical limits. Electrons need power, they generate heat. Cooling it all down is getting really, really tough.
It is. You can only push electrons so fast and pack them so densely.
So the next big jump, it seems like it has to sidestep the electron altogether.
That's where light comes in. Photonics.
Exactly. And that's what we're diving into today, a really significant breakthrough from USC's Viterbi School of Engineering. They've created the first optical device based on this totally new idea called optical thermodynamics.
Yeah, this is potentially huge. So for you listening, our mission today is to really unpack how this changes the game for photonics. It taps into, the fundamental properties of light itself.
How light can, and this sounds almost like science fiction, how it can autonomously route itself.
That's the core idea, getting rid of those complex, power-hungry switches, the electronic bottlenecks. This is about letting light find its own way.
Okay, so the central finding, just to state it clearly up front, light doesn't need to be forced. It can find its own path through a system, and it's driven purely by, well, the basic laws of thermodynamics.
Which could lead to optical tech that's not just faster, but just more natural, more efficient by design.
Right. Okay, let's maybe start with the challenge itself, the routing problem, because that's really the speed bump we're facing now, isn't it?
Absolutely. I mean, think about any engineered system. Routing fluids, routing data, you always need control. Switches, valves.
Like in electronics, you've got routers, network switches.
Yep.
They look up where data needs to go and then physically, well, electronically steer it.
Yeah, they receive a packet, check an address table, execute a command, send it this way, not that way.
And in photonics, traditionally, we've kind of just copied that model, right? We built optical versions of electronic switches.
Pretty much. Using these really complicated arrays of tiny physical switches, often needing electronics to control the optical path anyway.
Which seems counterintuitive if the goal is pure optical speed.
Exactly. Directing light accurately and quickly, that's always been the Achilles heel. Relying on external controls, converting optical signals to electrical just to make a decision, then back to optical again, or using tiny moving mirrors.
That sounds slow and power hungry.
It is. It introduces delay, latency, and consumes a lot of power. Plus, building these things is complex. It's not just hard to make, it's the fundamental thing holding back performance, especially in, dense systems. Think data centers.
So we're spending all this effort, all this energy, just guiding the light step by step through the maze. But this USC work, it suggests the guidance system should be built into the maze itself. They came up with this completely fresh approach, and the analogy they use is fantastic. A self-moving marble maze.
I love that analogy.
Yeah. Think about it normally. You tilt the maze or guide the marble. But here, the idea is the maze itself is structured, designed, so that no matter where you drop the marble, the light, it just naturally rolls to the right exit.
The path is kind of predetermined by the structure, by the potential landscape, if you will.
So the light finds the right path all on its own, driven purely by its thermodynamic behavior. Is that right?
That's the core concept. It's a self-organizing system. It doesn't need an external digital command saying go left or go right. That's why they call it autonomous routing.
And the driving force isn't an electronic signal, it's thermodynamics.
It's the light's inherent tendency, you could say. Its desire to settle into an equilibrium state. And that state is defined by the device's physical architecture.
Okay, this clearly needs a deeper dive, this idea of optical thermodynamics. What exactly is it?
Right. So this is the theoretical framework the USC researchers in the Ming-Shi Department of Electrical and Computer Engineering developed. It's specifically designed to describe how light behaves in nonlinear optical systems.
And those nonlinear systems, they've traditionally been seen as problematic, haven't they?
Oh, absolutely. They were kind of the black sheep of photonics. Engineers often actively avoided them.
Why? What's the issue with nonlinearity?
Well, when light travels through certain materials, especially at high intensities, its properties can change the properties of the material, which in turn affects the light itself. It gets complicated. And in multi-mode systems, where light can travel in many different patterns or modes simultaneously, the interactions between these modes in a nonlinear material become incredibly complex. It looks chaotic, random almost. Hard to predict where the energy goes.
So uncontrollable, is that the perception?
Pretty much. That was the standard view. Too chaotic, too unpredictable, fundamentally hard to simulate accurately, let alone design for any practical use.
But the USC team saw something different.
Exactly. They had this key insight. These systems, precisely because they aren't limited by the simpler rules of linear optics, they actually contain a huge amount of, well, richness, unexplored potential.
So the complexity isn't just noise, it's information.
Right.
Or structure.
It can be structure.
Mm-hmm.
They realize that the light interacting within these complex systems undergoes a process that looks remarkably like a system reaching thermal equilibrium.
Okay, like thermodynamics in gases.
Yes, that's the analogy. Think about how gas molecules bounce around and it looks chaotic, but statistically, they settle into a predictable distribution of energies and positions, thermal equilibrium.
And they're saying light does something similar in these nonlinear optical systems.
They're saying the mathematics describing that settling process, the tools of thermodynamics and statistical mechanics, can be adapted to describe how light energy distributes itself among the different modes in these optical systems. They found a way to tame the apparent chaos by seeing the underlying thermodynamic predictability.
Wow, okay. So how do they apply that? You mentioned analogies.
Right. To control the light's behavior, they use concepts directly analogous to familiar thermodynamic processes, things like optical expansion and compression, even optical phase transitions, within these specially designed nonlinear lattices.
That's a completely different way of thinking about light control, but maybe we should quickly touch on the basic physics of light itself here, just to ground this a bit. Photons.
Good idea.
Yeah.
Fundamental stuff. A photon, the particle of light, is a boson. It has a spin of 1.
And being a boson is key, right? Unlike electrons, which are fermions.
Crucially important. Bosons don't obey the Pauli exclusion principle. Fermions, like electrons, can't occupy the same quantum state that keeps their distance. Bosons, they're happy to pile into the same state. They can condense.
Like in a laser, sort of.
Sorta, yeah. It's related to that collective behavior. And photons, within the standard model of particle physics, they're gauge bosons. They mediate the electromagnetic force.
So when two electrons repel each other.
They're actually exchanging virtual photons. That's the mechanism of the force.
And we classify photons by energy, right? Radio waves, visible light, X-rays.
Exactly. It's all electromagnetic radiation, just different energy levels, which corresponds directly to frequency. Energy and frequency are proportional.
Which brings us to Planck's famous equation, E equals h nu.
That's the one. The energy E of a single photon is Planck's constant h times its frequency. It's quantized, comes in discrete packets.
And this energy can be transferred, obviously, like light warming something up.
Right. That photon energy gets absorbed, maybe knocks an electron loose, like in the photoelectric effect, or just increases the kinetic energy of atoms and molecules in a material. That increased kinetic energy is thermal energy. That's temperature increase.
Okay, so photons carry energy. They are bosons. They like to be in the same state. How does this thermodynamic framework use those properties?
It leverages that bosonic nature. In this nonlinear system, the interactions, the collisions between photons, mediated by the material, cause the energy to spread out among all the available modes. It's like the photons are exploring the space.
Like a gas expanding into a container.
Exactly like that. And just like a gas reaches a predictable temperature and pressure, the population of photons across these different optical modes settles into a predictable statistical distribution. It's an optical version of the Maxwell-Boltzmann distribution you see in gases.
So the chaos wasn't random noise, it was just the system naturally settling towards its equilibrium state.
Precisely. The key is that the researchers don't just let it settle randomly. They engineer the container, the nonlinear lattice, very carefully. They create optical analogs of temperature and pressure.
What represents temperature and pressure for light?
Intensity can act sort of like pressure, and the way energy is spread across the modes relates to temperature. By designing the geometry, the boundaries of the system, they can make one specific output channel the most thermodynamically favorable state, the lowest energy state for the photons to settle into.
And because photons are bosons and like to be in the same state at equilibrium?
They naturally condense or flow into that single designated output channel. The system is designed so that equilibrium means the light goes where you want it to go.
That is really clever. It's like making the physics do the engineering work.
It is, harnessing the natural tendencies instead of fighting them.
Okay, let's get back to the actual device they built. This isn't just theory. They demonstrated it, published in Nature Photonics. You mentioned it's inspired by Joule-Thomson expansion. How does that work for light?
Right, the Joule-Thomson effect in gases. That's when a gas expands through a valve or a porous plug.
Yeah.
If pressure drops and its temperature changes, it might cool down or heat up, depending on the gas and conditions, before it settles into a new equilibrium on the other side.
So in the optical device, the light enters the specially designed lattice. That's the valve.
Kind of, yeah. It enters this region where the nonlinear effects are strong, where the modes can interact intensely. This is the optical analog of expansion. The energy starts spreading out, exploring all the possible paths or modes.
Okay.
Then, as the light propagates further through the device, the structure is carefully designed. The geometry changes to guide the system towards equilibrium. And as we said, that equilibrium state is engineered to correspond to the photons collecting primarily in one specific output channel.
So it's a two-step process.
Yeah.
First, let the energy spread out, like expansion.
And then guide it gently towards the desired equilibrium state.
And that equilibrium state is the correct output. So no external switch needed to force it.
No external switch. The potential landscape of the material itself, shaped by the design and the light's own intensity, does the channeling. It creates this inherent flow path.
The light just follows the path of least, thermodynamic resistance?
Essentially, yes. It seeks the lowest available energy state, and the system is built so that state is the target output. We eliminate the control electronics, the complex switches. It dramatically simplifies the whole routing architecture.
The implications for industry here seem massive. You mentioned data centers earlier. Computing is really hitting that power wall.
It really is. Energy efficiency is becoming just as critical as raw speed, maybe even more so. Those optical to electrical to optical conversions we talked about, they burn a huge amount of power globally in data centers.
So if you can manage the light flow entirely within the optical domain.
The power savings could be transformative.
Oh.
Really significant.
The original research mentioned companies like NVIDIA are actively looking for better optical interconnects. How does self-routing specifically help there?
Well, think about connecting processors on a chip, or chips on a board, or servers in a rack. Right now, if you want flexibility, if you want to be able to route data dynamically between many points, you need lots and lots of complex optical switches.
Which adds cost, size, and power consumption.
Exactly. But if the routing happens somewhat automatically, based on the structure of the interconnect itself, you could potentially build much denser, faster, and more energy-efficient networks. They become more scalable. You're moving from actively managed networks to passively self-organizing ones.
It sounds almost too elegant. What about, say, robustness? Does this thermodynamic approach hold up under different conditions? Is it stable?
That's a great question, and potentially one of the strengths.
Yeah.
Because it relies on statistical equilibrium behavior, the average behavior of many photons, it might actually be more robust than systems relying on a single precise switching event. Well, it's less dependent on the exact state of every single photon at every instant. It's about the collective settling into equilibrium. This could make it less sensitive to small fluctuations in temperature or input power compared to, say, a tiny mechanical mirror that needs to be positioned perfectly.
Interesting. So the statistical nature actually provides stability.
That's the idea. It harnesses the complexity, makes it work for the system rather than against it.
Which leads back to that core benefit you mentioned, making devices that are somehow both more powerful and less complex at the same time.
Right. It's a fundamental shift in design philosophy for these kinds of optical systems.
I was struck by a quote from the lead author, Hediye Danani. She said, "This framework enables entirely new approaches to light management, impacting not just information processing, but maybe even fundamental physics."
It really opens up the design space.
Oh.
And Professor Dimitrios Christodoulides, who's a major figure in this field involved in the research, he put it really well. He said that what everyone used to see is this intractable challenge in optics, this messy, nonlinear mode coupling, has been completely reframed. It's now seen as a natural physical process. And once you see it that way, you're not fighting physics anymore. You're using it. The burden shifts from complex external engineering to clever internal design that leverages the natural laws.
That really is a profound shift, using the inherent nature of the system itself.
It is.
Which does leave you wondering, doesn't it? If this seemingly chaotic mess of light modes in a nonlinear system can be understood, predicted, and even engineered just by applying thermodynamic thinking, well, what other complex systems are out there? Maybe in physics, maybe in information transfer, even things like quantum systems, or maybe aspects of AI. Could they also be waiting for a similar kind of reframing? Could applying principles like equilibrium and statistical mechanics unlock new ways to understand and control them too?
That's a really interesting thought. Where else might thermodynamics hold the key to taming apparent chaos?
Something for all of us to mull over. Thanks for breaking that down today.
My pleasure. Fascinating stuff.